issues in measuring correlation. When we talk about using statistical models to examine an outcome, the model explains some explanation about the outcome. What the model cannot explain about the outcome is denoted as errors. If we focus on the model, in the model there are variables that we use to explain the outcome. We look at the relationships between variables, and to look at these relationships between variables, we can use covariance. If there are two variables, we can use covariance and establish an unstandardized relationship using the raw values, raw measured values. We can standardize those measured values by standard deviations of each variable and then establish a relationship that's called the correlation and come up with a correlation coefficient about the strength of the relationship. When we have multiple variables, we can also look at a relationship in another way using a method called regression method. In that, we can look at the slope between two variables. If there are only two variables, a predictor variable and outcome, we can look at it in an unstandardized or standardized way. If you look at correlation and the regression, correlation explains the extent of the linear relationship. Either it is perfectly linear or not linear, and that perfect linearity could be in the opposite direction between the two variables. One increases, the other decreases, or the perfect linear relationship could be in the same direction. One increases, the other one increases. Or there's no relationship at all, linear relationship. So these values can vary from -1 to 0, which is no relationship, to +1. So the -1 to +1, to the two extremes, are perfectly linear relationships, and the 0 as you come to the middle shows that the linearity decreases, and 0 means there's no linearity in the relationship. It's about how easy to draw the best fit line between the variation of the predictor in relation to the outcome. If you look at the chart here, we can see that the blue dots, where there's an outcome, the outcome keeps changing with the variation in the x variable. The y keeps changing where the 2 points meet and the data points are shown in dots. And we can join those dots very linearly, very easily, and draw a linear line. That means the strength of the linearity of the relationship is extremely high. You can see that the correlation coefficient is 0.995. But if you look at the orange line, we can see the data points, the outcomes in relation to the variation in X are quite dispersed. And if we draw the best fit line, we can see that some of these dots are far away from the best fit line. So the linearity is far less than the blue line. So the correlation is 0.873. The regression, which is identified by the slope, shows the steepness of the linear relationship. How deep is the relationship? So it can vary from minus infinity to plus infinity. And 0 means there's no steepness in the relationship. So the regression slope indicates to us how steep is the best fit line. And if the line is very steep, that means there is a steep relationship between the two. For example, if we take the blue line, we can see the slope is 2.847. If we take the orange line, the slope is 5.951. In other words, it is the impact that X variable has on the Y variable. When X changes by 1 unit, the slope indicates in the blue line that the Y changes by 2.847. And in the orange line, when X changes by 1 unit, Y changes by 5.951. So it shows the impact, the extent of the change or the deepness of the relationship. And how steep the line or the angle is shows the steepness of the relationship. Previously, we looked at the variables. The variables are in the model. But in the statistical model investigation, there's model and also errors. Some of these errors could be explained, which are called the residuals. And they also have an influence on the outcome. This is the model and the errors together explains the outcome. So if you look at the errors now, we expect the errors, the residuals which can be identified in errors, and if we plot against the predicted outcome, errors should be normally distributed and should be independent of each other. That means if we take the outcome variable in the x-axis here, this is the left chart, and then draw how the residuals change and draw a best fit line for the residuals, the residuals do not change with the change in the outcome variable. They are consistently away from the outcome observation for each outcome position. These errors are normally distributed across the best fit line. But we can have a situation which is shown in the right side of the chart. On the right side chart shows where the errors looks like they are distributed normally, but in fact some of these errors keeps changing with the outcome. They go up and they go down and then go up, because the ups and the downs, when you take the difference, they become equal. So we can draw a horizontal line, but that horizontal line, as for the residual, is elusive because it keeps changing, is not evenly distributed. The net effect is zero, but at a given point, at different points, there's some aggregation, concentration onto one side or the other, if you take that residual line. This situation is called the serial correlation or autocorrelation of errors. So these errors can arise due to various reasons. If you are looking an outcome or a long period, these errors can persist over a long period as well. These errors can be generated due to 4 factors. First one is omitted input variables. So there are variables that should have been included in the model that are not included. Then they become part of the errors. And while they are there, which is outside the model being investigated, they can have an influence on the outcome. Second is the omitted variable bias. There could be a variable that is omitted, which is now in the error portion of the model. But these omitted variables can have a relationship with the existing variables in the model, with the input variables. By that, the errors are exercising an influence on the model outcome. The third is functionally misspecifying the model. It may be such that when we look at the relationship between the independent variable and the dependent variable and then plot the data points where they intersect, maybe they actually don't fit into a linear relationship, but rather they fit into a non-linear relationship. So if we draw a linear line, or if we examine the model linearly, then the true effect of those predictor variables or input variables are not captured. The true effect is not captured. So that means we are using a functionally misspecified model. We're using a linear model. In fact, we should have used a nonlinear model. So that functional misspecification is now included in the error portion. Fourth is that we may measure the existing variable erroneously. And when we measure existing variables erroneously, they generate errors, and those errors can be included in the error portion in the model. And all these errors can be persistent over time, and can have an influence not only in the period that we are investigating, but over a longer period as well. So how do we overcome autocorrelation? One is to include a lag-dependent variable as input variable. It could be that the dependent variable has been influenced by the errors, and that previous dependent variable or the dependent variable relating to the previous period is influenced in such a way. And in the current model, when we examine the current period, we can then, if we have the information, we can include the previous outcome as an input variable to mitigate the effect of errors, because the previous outcome has been affected by the errors. The second is we capture the trends or the seasonal variations using a statistical model. Using, for example, a linear model. It could be a regression model, or it could be exponential smoothing or differencing model. And we find out the relationship. And then we want to find out whether there's some more information or some more explanation that we have not captured. And for that, as a second model, as second stage, we can look at for the autocorrelation using models such as autoregressive or autoregressive moving average model, ARO, ARMA models, for the already detrended model. We can also use autoregressive integrated moving average ARMA models as well, but they are used for forecasting only. What we do in that situation is we run that model, the first model, and then that model offers an explanation, but there's an error portion. We take that errors, which are now the errors that we have found out, and from these errors, we forecast we estimate another set of errors, thinking that they are autocorrelated. They have a relationship. The previous errors, we are estimating whether they are correlated with the current errors. If they are persistent, then there should be a relationship. Then we take the actual errors that we have found for the first model and we forecast or estimate another set of errors for the second model, and we take the difference of the errors of errors. And if that can offer a further explanation, then we can improve our existing model. For example, we have a forecast outcome or predicted outcome from the regression model. And now from the second model, we found the forecast error estimate as the errors of error or the difference of errors. And then we can add the difference of errors into the forecast outcome or the predicted outcome. And that errors of errors is additional information about the outcome that improves the outcome accuracy. So these are some ways where we can overcome autocorrelation.